Welcome all students. We are discussing the Satellite Communication Unit 1, the overview of the satellites. The topic to be discussed over here today is types of orbits for the satellites and examples of satellites. Up to now, in the last session, we have discussed the introduction of satellite communication, basic fundamentals, application of the satellites, and frequency allocation of a satellite. In this session, we are going to see the types of orbits and examples. So let us start. Start with types of satellite. We are classifying the satellites based on their orbits. So most important, geostationary or geosynchronous Earth orbit, GEO. Generally we can say that if we are at some point at the Earth, the satellite remains stationary at that point, as you can see in this figure. A particular animation shows a particular point and a particular satellite which is in the same state at all time. Technically we can define this: GEO satellites are synchronous with respect to Earth. Looking from the fixed point from the Earth, these satellites appear to be stationary. These satellites are placed in a space in such a way that only 3 satellites are sufficient to provide the connection throughout the surface of the Earth. Their footprint is covering almost 1/3 of the Earth. The orbit of satellites is a circular. There are 3 conditions which lead to geostationary satellites. Lifetime expectancy of these satellites is nearly 15 years. First, the satellite should be placed at 37,786 kilometers, approximately 36,000 kilometers above the surface of the Earth. These satellites must travel in the rotational speed of the Earth and the direction of the motion of the Earth, that is eastward. Means satellites have a same duration of a rotation of the Earth as our in its orbit. Third, the inclination of satellite with respect to Earth must be 0. Means it will be 0 degree with respect to equatorial plane. Fine. So it is very easy to understand. The geostationary means a particular satellite remains stationary at some point. Geostationary satellites in a particular is termed as a geosynchronous, as there are multiple factors which make this satellite shift from its ideal geostationary condition. Just like a gravitational pull of the sun and moon makes the satellites deviate from their orbit. Over the period of time, they go through the drag. Earth's gravitational force has no effect on these satellites due to this distance of the surface of the Earth. These satellites experience the centrifugal force due to the rotation of the Earth, making them deviate from their orbit. Third, the non-circular shape of the Earth leads to continuous adjustment of the speed of the satellite from the Earth station. Means there are some condition or there are some controls required for our geostationary or geosynchronous satellite to remain in our orbit. These satellites are used for a TV and radio broadcast, weather forecast, and also these satellites are also operating as a backbones of the telephone networks. So it have many advantages, but as you know, there are also some disadvantages of this GEO orbit. Let's discuss. Northern or southern regions of the Earth poles have more problems receiving these satellites due to the low elevation above its latitude of 60 degree. Larger antenna are needed in this case. Shading of this signal is seen in this city due to a high building and low elevation further away from the equatorial limit transmission quality. The transmit power needed is relatively high, which causes problems for battery powered device. These satellites cannot be used for a small mobile phones. The biggest problem for a voice and also data communication is the high latency, as without having any handovers, the signal has to at least travel 72,000 kilometers. Due to the large footprint, either frequencies cannot reuse or the GEO satellite needs special antennas focusing on a smaller footprint. Transferring a GEO into orbit is very expensive. So there are some pros and cons we have discussed. Let's go ahead. Another type is low Earth orbit. A particular orbit is shown in this figure is in the red color. A red orbit shows the LEO satellite orbit. These satellites are placed nearly about 500 to 1000 miles above the surface of the Earth. As LEO circular as a lower orbit, hence they exhibit a much shorter period than the 95 to 120 minutes. LEO system try to ensure a high elevation for the every spot on the Earth to provide a high quality communication link. Each LEO satellite will only be visible from the Earth for a ground of around nearly 10 minutes. Using the advanced compression scheme, transmission rate of about 2400 bits per second can be enough for a voice communication. LEOs even provide this bandwidth for mobile transmitters, and which have a omnidirectional antenna using the low transmit power in the range of 1 watt. The delay for the packets delivered via LEO is relatively low, approximately 10 milliseconds. The delay is comparable to long distance wired connections, about 5 to 10 milliseconds. Smaller footprints of LEO allow for a better frequency reuse, similar to the concept used for our cellular networks. LEO can be provide a much higher elevation in the polar regions and so better global coverage. So there are some good points for LEO satellites. These satellites are mainly used in the remote sensing and providing a mobile communication service due to its lower latency. It has also some disadvantages. Let us discuss some disadvantages of the LEO orbit. The biggest problem of the LEO concept is the need for the many satellites in a global coverage, so it is to be reached. Several concepts involved 50 to 2000 or 200 or even more satellites in the orbit. The short time of the visibility is in the high elevation requires additional mechanism for a connection handover between the different satellites. The high number of satellites combined with the fast movements resulting in the high complexity of a whole satellite system. One general problem of LEO is the short lifetime of about 5 to 8 years due to the atmospheric drag and radiation from the inner Van Allen belt 1. Assuming 48 satellites and a lifetime of 8 years, the new satellites would be needed every 2 months. The low latency via a single LEO is only half of the story. The other factors are also needed for the routing of the data packets from satellite to if a user wants to communicate around the world. Due to the large footprint, the GEO typically does not need this type of routing, as sender and receivers are most likely to the same footprint. So we have discussed the LEO satellites. Let's go ahead and let's move further from the Earth's surface. Is called as a medium Earth orbit satellites. Medium Earth orbit satellites is above the LEO. So MEO can be positioned somewhere between LEO and GEO. As shown in this figure over here, it is above the LEO and below the GEO, both in terms of their orbit and due to their advantages and disadvantages. Using orbits around 10,000 kilometers, a system only requires a dozen satellites, which is more than GEO system but much less than LEO system. These satellites move more slowly relative to the Earth rotation, allowing a simpler system design. Satellite periods are about 6 hours. Depending on the inclination, the MEO can cover larger populations, so require fewer handovers. It also have some drawbacks. Again, due to the larger distance to the Earth, delay increased to about 70 to 80 milliseconds. The satellites need higher transmission power and special antennas for the smaller footprints. The above three are the major three categories of the satellites. Apart from this, the satellites are also classified based on their following types of orbit. As we can see, a particular highly elliptical orbit shown in the green line, a particular LHEO have a different variations, and an HEO is oblong with one end nearer to the Earth and other is more distant. Means one point is called as a apogee, other point is called as a perigee. The satellites in the LEO are suited for the communication, satellite radio, remote sensing and other application. Another type of satellite orbit is sun synchronous orbits. This animation shows the sun synchronous orbit satellites working and its coverage area. Let's define sun synchronous satellite. These satellites rise and set with the sun. Means it will synchronize with our sun time. Their orbit is defined in such a way that they are always facing the sun and hence they never go through an elliptical. So a particular figure is shown over here that satellites faces each and every time to the sun. It never go to the dark side of the Earth. Fine. For this satellite, the surface illumination angle will be nearly same every time. The surface illumination angle shows that the illumination angle is the angle between the inward surface normal and the direction of the light. This means that the illumination angle of the certain point of the Earth surface is 0 if the sun is precisely overhead, and that is 90 degree at a sunset and sunrise. Special cases of the sun synchronous orbit are the non or midnight orbit, where the local mean solar time of the passage of for equatorial latitudes or longitudes is around the noon or mid time, and the down dusk orbit, where the local mean solar time of a passage for equatorial longitude is around the sunrise or sunset. So that the satellite rides that terminator between the day and night. As you can see in this figure, our sun synchronous satellite covers the entire Earth in this fashion. So it will cover each and every area of our Earth by its orbit. I think this animation will help you to understand the working of sun synchronous. Let us see again. So our satellite move in this direction, and it will cover the area. It is our India. Turn by turn it will cover entire region. From next it will show the coverage area. Look at the sun moving in this direction, our satellites also in the same direction. Look at this. It is a sun. It is a day. Okay, let's go ahead. The next is Hammond transfer orbit, or we can say Hammond transfer orbit. It is an intermediate orbit having a highly elliptical shape. It is usually used by the GEO satellites to reach their final destination orbit. Means it is a transitional, we can say that, orbit. It is used by the GEO satellites to reach their final destination orbits. This orbit is connected to the LEO orbit at the point of the perigee, forming the tangent, and it is connected to the GE orbit at the point of apogee, again forming the tangent. So there is a two important term, apogee and perigee. We are going to see one good video I found in YouTube for the Hammond transport orbit. Let us see that video.
Welcome to this LabRat Digital Lab. Today we want to talk about how to transfer from one orbit around the Earth to another higher orbit to make a rendezvous with something like the space station. To do this, we'll use the Hammond Minimum Energy Transfer Orbit. What do I mean by a transfer trajectory? First of all, here's my simple circular orbit around the Earth. This is my original orbit that I start off in. But what I ultimately want to do is achieve a higher orbit to rendezvous with a space station. Now to do that, I need to go from the lower orbit to the higher orbit, and I use an elliptical transfer orbit. The Hammond transfer is a minimum energy transfer, which means I need the least amount of delta V, the change in velocity, to get me to move to the higher orbit. Here's my spacecraft, and the first thing I need to do is fire rocket motors to change the delta V of the vehicle to pick up the new elliptical transfer trajectory. So I only fire my rocket motors for a brief period of time and then coast most of the way to apogee of the transfer ellipse. Now, if I don't do anything at this point, the spacecraft will continue to follow along the elliptical orbit, and I will not achieve the desired circular orbit at the higher altitude. Let's try this transfer again. Now this time, I only want to use half of the transfer orbit, because I want to fire my rocket motors at apogee to achieve the new desired circular orbit at the higher altitude. Once again, I fire my rocket motors to enter into the transfer ellipse. I only burn my rocket motors for a short period of time, and again, coast until apogee. Now, once at apogee of the transfer ellipse, I need to reorient my spacecraft and fire my rocket motors once again to add delta V to the trajectory to circularize the orbit at the desired altitude. Once I do that, my engines cut off and I coast and remain in the new higher circular orbit. As I said earlier, the Hammond transfer is a minimum energy transfer, which requires the least amount of delta V, but it also takes the most time to get from the inner orbit to the outer orbit. It is possible to have a faster transfer orbit, but that means I'm going to have to add more delta V at the lower orbit, then have a higher delta V in order to change the velocity to achieve the new higher circular orbit. And that's depicted in the figure at the right. Now this requires more delta V, which requires more propellant, which makes the rocket heavier and more expensive. So ideally, we like to use the Hammond transfer to do things as efficiently as possible.
So students, you have understand the Hammond transfer orbit. This orbit is used by for our transmitting our antenna or transmitting our rocket from one orbit to the another orbit which have a minimum energy. Let's go ahead.
Welcome to this lab.
Another type is prograde orbit and retrograde orbit. A particular animation shows the prograde and retrograde with each term. Shortly I explain you, a prograde orbit have a same rotation to the Earth, and the retrograde have a same but 190 or 90 degree rotation than Earth. Prograde orbit. This orbit is within an inclination or less than 90 degree. The direction is the same as the direction as the rotation of the primary planet, just like our Earth. In the retrograde orbit, this orbit is an inclination more than 90 degree, and its direction is counter to the direction of the rotation of the planet, just like our 90 or 180 degree reverse of our planet's rotation. Only few satellites are launched into this retrograde orbit because of the quality of the fuel required to launch them in a much greater than the prograde orbit. This is because when the rocket starts out the ground and it already in a eastward component of the velocity equal to the rotational velocity of the planet is launched the latitude. Fine. This animation shows you the rotation of the each orbit. So it is a anti-clockwise and this is a clockwise. Both are reverse of each other. This figure also shows you the prograde and retrograde orbit. A particular blue line shows our Earth rotation and the red satellite shows the retrograde orbit. In the dark epicenter, our Earth is moving in this direction. It is our one satellite which is in the prograde orbit, and the outer layer, just like our orange dot, is in the reverse direction of our Earth rotation. So with this animation you can understand it very clearly. Let's go ahead. Polar satellites. This orbit passes above both planes, north and south pole of the planet of each of its revolution. Therefore, it has an inclination very close to 90 degrees. These orbits are highly inclined in a shape. Means a polar orbit comes in this fashion as seen in animation, that it can pass each pole one by one to cover the entire area of our Earth. So look at this. It will cover each and every component, each and every portion of our Earth. A gap is filled by each revolution. Once again we can see the same animation. Look at this. In each revolution it will cover some portion of the Earth. In the another revolution it can also cover. After rotating and after the covering all the area, we can make the whole diagram with the help of the softwares. Okay, let's go ahead. Up to now we have seen the different orbits of our satellites. Now let's have some look the examples of some satellites in its early stages. First is INTELACT, or International Telecommunication Satellite. It is created in 1964 and it will cover and it will have a member of 140 countries, and more than 40 investing entities are there. The early bird satellite is 1965 launched. 6 evolution of international telecommunication satellites between 1965 to 87 is launched. It will use a geostationary orbit. As you have already seen the geostationary orbit. This covers 3 regions: Atlantic Ocean region, Indian Ocean region, and Pacific Ocean region. Another example is US DOMSAT or domestic satellite. It uses geostationary orbit. It have over 140 members countries. It provides direct to home TV services. It have three categories: US DBS system, high power, medium power and low power. It measures in equivalent isotopic radiated power EIRP. The upper limit of EIRP is high power have a 60 dB watt, medium have a 48 dB watt and low power have a 37 dB watt. Another is polar orbiting satellites. These satellites use a weather forecasting or weather monitoring between 800 to 900 kilometers above the Earth's surface. It have a ultraviolet sensor, also measures the ozone level. A particular NOAA, National Oceanic and Atmospheric Administrator, operates a weather satellite system. It have a period of 102 minutes and Earth rotation at a 25 degrees. Estimate the subsatellite point at the following times after the equator of 90 degree east north-south crossing. First, 10 minutes at 87.5 degree east and 36 degree south. It have a 102 minutes duration at 65 degree east and equator, and it have a 120 minutes at 60 degree east and 72 degree south. Fine. The system use both geostationary operation environment systems satellites GOES and the polar operation environment satellites POES. The sun synchronous they grow across the equator at the same local time at each day. The morning orbit, a latitude of 830 kilometers, crosses the equator from south to the north at 7:30 am, and the afternoon orbit at altitude of 870 kilometers at 1:40 pm. It can be used as a search and rescue satellite, just as a COSPAS SARSAT. So, we have seen some good examples of satellites with their function. Up to now, we just summarize our discussion and what we have learned from this discussion and the previous discussion. So let us summarize. This discussion shows the basics of satellites and elaborating the parameters which are needed to calculate the distance of the orbit to which a satellite is to be launched and other factors which are necessary to the define an orbit. Further, this unit discusses the application of the satellites and elaborates the global communication which has now become the possible due to the presence of the satellites. This unit also elaborates the frequency bands used by the each communication satellites. Going further, this unit also elaborates on the types of the orbits a satellites can follow to provide a communication. The last segment of this unit discussed the three examples of satellites revolving around the Earth. So students, you have brief idea about our satellite communication, its basic concept, its orbit, frequency and its examples. These are the questions you have to write in your notebook and send back it to me as per the given directions. These questions are very important for your understanding and for your study purpose. Okay, let's conclude this session. Thank you everyone. See you in the next session.